This lesson is about magnetism. First, I'm going to deal with properties of magnet. And a magnet, when cut into pieces, when freely suspended, always comes to rest in north-south direction. The magnet, when cut into pieces, also every piece will exhibit polarity. Okay, and the magnetic induction precedes attraction. This is north pole, south pole means this becomes south and this becomes north. Attraction, munnadiye induction is happening. Induction precedes attraction. These are the 3 points. Then the next thing that I want to teach you is certain terms which never comes in any exams. What is magnetic axis? A magnetic axis is nothing but the distance between the north pole and the line joining the north pole and south pole passing through the center. What is magnetic meridian? Magnetic meridian is the vertical plane passing through the magnetic axis, is known as magnetic meridian. Okay, next is magnetic length. A length is the distance between the north pole and the south pole, which is always 2L. It's never L. Then is about magnetic dipole moment. Magnetic dipole moment. It's represented by capital M, which is either of the pole strength. You know, a magnet will have a pole strength M1 and an M2, but is always considered to be equal. Okay, because north pole and south pole strength same ada. So it's either of the pole strength into separation. So it's a vector because 2L is a vector. Let's look at the unit. I know magnetic moment is near from the last chapter. Number of turns doesn't have any unit. Current is ampere and area is meter square. So I know that this is ampere meter square. So pole strength or unit ketangana, this is meters. Meter square get cancelled. Therefore, a pole strength or SI unit is ampere meter. Whereas magnetic moment SI unit is ampere meter square. However, there's one more unit called joule per Tesla. Joule per Tesla is another unit, and I'll tell you how it came later. Okay, so then there are 2 units. Ampere per meter square is the main unit for me. There's also joule per Tesla, which is not net unit. Okay, so now this is ampere meter. Then I'm going to talk to you about magnetic field lines. How to draw magnetic field lines. You know, from outside the paramagnet goes from north to south. Within the paramagnet goes from south to north. Outside paramagnet goes from north to south. Within the paramagnet goes from south to north. Continuing like this. So this shows that there's a uniform magnetic field within the magnet. So between south pole, it's parallel field, right? So uniform magnetic field exists between north pole and the south pole, and the degree of closeness indicates the strength of the magnetic field. No 2 lines cross each other. If it does, it indicates 2 directions at one point, which is not possible. And magnetic field lines always form a closed loop. So these are the properties of the magnetic field line. Defined magnetic field line is a path taken by unit north pole. Taken by unit north pole in a magnetic field. So you would have drawn these lines in 9th standard or 10th standard, where you'll keep a compass needle around a magnet, and the north pole or a path you will plot and you will draw these lines. You must have done this. 1 second, hold on. So next the magnetic field lines. I taught you about axial line and equatorial line. You have a bar magnet. Always keep north here and south here. This is called the axial line. At any point P, which is at the position vector R from the center. That's the reason we call this as L and L, 2L. So that this distance from the north pole is R minus L. This distance from south pole is R plus L. And you have, when you see north pole, it's going to have a magnetic field which is pointing away. And when you see a south pole, you have magnetic field B south. And we're going to do B north minus B south. Why B north minus B south? B north is more effective because B is inversely proportional to distance. The distance is short. B is more. பக்கத்தில் இருந்தால் magnetic field அதிகமாக இருக்கும். அதனால B north minus B south, which itself is going to become mu naught by 4 pi into pole strength by R minus L the whole square minus mu naught by 4 pi into pole strength by R plus L the whole square. So what's common is this. And when I take 1 by R minus L the whole square by 1 by R plus L the whole square and take LCM, it will be R square minus L square the whole square, and this will become 4RL, 1 of the small m and a 2L. will become capital M, so it will become 2 capital M. Mu naught by 4 pi into 2 capital M into this small r which is there by r square minus L square the whole square is the magnetic field along an axial line. In my opinion, it is going to take the direction of B naught because that's more powerful. Okay, நான் உனக்கு 4 ரூபா கொடுக்குறேன், நீ எனக்கு 2 ரூபா கொடுக்குறேன்னா 4 ரூபா தானே ஜாஸ்தி, அந்த மாதிரி B naught is greater, so it's going to be along positive y direction in this diagram. Okay, and that's going to be a Tesla and the magnetic field along an axial line. So considering a case study where r is much larger than L, you can write it as mu naught by 4 pi into 2 m r by r to the power 4, ignoring the L square, r and r, it will become r cube, and this is what is the formula. Then is the equatorial line. Let's talk about equatorial line. You have a bar magnet, this is the equatorial line which is at a point P, which is at a position vector r, and this side is L and this side is L. This is north pole, this is south pole. The magnetic field B north will come like this, the magnetic field B south will go like this, and if this is theta, this is theta, then you mark this line and mark this as theta. Physics la edu slanting ah irundhalum it will get broken down into B naught sin theta and a B naught cos theta. Similarly, the one which is like this, which is due to south, is going to break down into B south sin theta and a B south cos theta. The vertical component is getting cancelled and the horizontal component is getting added up, which is B north cos theta plus B south cos theta, which is B north plus B south into cos theta. And you know this distance is root of r square plus L square. This distance is also root of r square plus L square. Pole strength is the same. So then magnetic field of B north and B south will just be the same at this point because same distance, same pole strength. So you can write 2 times B cos theta, which is 2 into mu naught by 4 pi into small m by, the distance is this distance from this end, correct? Root of r square plus L square the whole square, root and square get cancelled. What is cos theta from this triangle is r by root of r square plus L square. So you know 2mr becomes capital M. Mu naught by 4 pi into capital M, this is going to become r square plus L square whole to the power 3 by 2. And that's for the equatorial, and it's along minus I direction because it's going from north to south. Can you see this direction going from north to south? Always remember, that's very important. Equatorial is always from pointing from away from north to south. So therefore the angle between the axial and equatorial is anti-parallel. That was I and this is minus I, so 180 degrees the angle between the magnetic field due to axial and the magnetic field due to equatorial. And also you know the axial is 2 times B axial is 2 times B equatorial is the conclusion. Then now what you do, take a uniform magnetic field and place a magnetic dipole here, and you know this is north pole and this is south pole. The distance is 2L making an angle theta. The perpendicular distance you should know is 2L sin theta. It will execute torque. அப்படி சுத்த ஆரம்பிச்சிடும். So the torque is equal to force into perpendicular distance. In reality, torque is R cross F. It's a cross product. However, you can write force into perpendicular distance. So force from E is equal to F by Q, F is equal to E into Q as per the first lesson, electrostatics. In magnetism, it's going to become B into small m. The electric field is becoming a magnetic field, charge is becoming pole strength. So B m into 2L sin theta, 2L m is capital M. So thus you get m cross B is the torque. And theta is 90, the torque is maximum, it is Bm. And theta is 0, the torque is also 0. So now we are going to do the potential energy derivation. Potential energy is nothing but torque into d theta is du. Torque itself is mb sin theta d theta. I'm going to integrate sin theta and integrate left hand side, you get minus mb cos theta integrated from theta 1 to theta 2. Upper limit minus lower limit is cos theta 2 minus cos theta 1. We are considering the initial position of the dipole is 90 degree and it's tilting through an angle theta. Theta 2 is theta, theta 1 is 90. So it will become minus mb cos theta to be the final formula based on this condition. And here comes, we're going to write stable and unstable condition from this. When theta is equal to 0, potential energy is minimum and is minus mb, which is the minimum potential energy. When theta is equal to 180, this potential energy is maximum, which is a plus mb. High energy andale unstable da. So this is unstable equilibrium, whereas this is stable equilibrium when theta is equal to 0. Are you clear? Next is very very important question. This question I taught you with a solenoid yesterday. We just have to write, instead of M, we should write Nia. And instead of B, you should find the magnetic field of solenoid using the previous lessons formula, mu naught into small n into I. We'll come back to that later. So this is what it is. Next thing that I taught you is about a magnetic moment of a revolving electron in hydrogen atom. Okay, so you're talking a hydrogen atom in which there is an electron which is revolving around the nucleus. When the electron is revolving like this, you know that the current will flow like this. And according to right hand thumb rule, when you keep the curled finger in the direction of the current, you know that the magnetic moment is downward. The angular momentum will be upward. The question is to find the magnetic moment. You start the derivation using M is equal to Nia. Number of turns, we're going to take it as one rotation. The electron is going to revolve only once. So take it as IA. I is equal to Q by T into area is pi r square, considering this is radius. T is time period because only one revolution. Velocity is distance by time, which is 2 pi r by T. Time period is 2 pi r by V. On substituting 2 pi r by V, pi and pi, r and r get cancelled. You get QVR by 2, which is the first formula for magnetic moment for doing the numerical unit. And VR is L by M. Okay, Q by 2M into L vector with a negative sign to indicate that the angular momentum is opposing the magnetic moment. They both are in opposite direction. You indicate a negative sign. How did you get that? Angular momentum is R times linear momentum. R into MV. So VR is L by M. Substituting that, you get a formula like this. This is charge by mass ratio. And this is the second equation. We should know to do the sums. And you also know from last year, L is equal to NH by 2 pi. So substituting that, you will get minus Q by 2M into NH by 2 pi. So it will become 4 pi M. In this you write N is equal to 1. You get M is equal to minus Q is nothing but charge of an electron, H by 4 pi M, where E is 1.6 into 10 to the power minus 19. H is 6.6 into 10 to the power minus 34, Planck's constant, 4 into 3.14 into mass of the electron is 9.1 into 10 to the power minus 31. You get Bohr's magneton. Bohr's magneton. And unit is, you can write ampere per meter square or joule per Tesla. How did you get joule per Tesla? From here, you know, the magnetic moment is also potential energy by B. Potential energy is also joule by B is Tesla. So that is how you get one more formula as a unit, joule per Tesla from here. When you treat it as a magnet, it is joule per Tesla. When you treat it as a coil, it is ampere per meter square. So that's about it. Bohr's magneton. I know this value itself is 9 into 10 to the power minus 24, I think, Bohr's magneton. No, I didn't teach you that. We'll check on that value a little later. So then let's go to next. What's the next thing that I taught you? They'll ask you a innumerable number of numericals based on this formulas, okay? The next thing that I taught you is B, H, and yes, I'm going to teach you what is B, what is H, what is I, what is susceptibility. B in general is magnetic induction or magnetic field strength, correct? Magnetic field strength, which is actually Tesla, which according to us is unit is Weber per meter square. So I can simply say flux passing through unit area. But however, they won't accept this answer. They'll expect you to write B in a medium. Magnetic field of a medium is proportional to the H, which is magnetic field intensity. So H is nothing but magnetic field intensity. Okay, I'll come back to this. B is equal, since it's a medium, it's mu into H, not mu naught into H, is very first equation. Next is magnetic field intensity is field related. Field, how strong is the field? Field related. So the extent to which a field can magnetize a substance. But if you say this definition, they won't accept. They'll expect you to write ampere turns per unit length. Don't forget that. Per unit length. So SI unit is ampere per meter. Then this is called intensity of magnetization. Intensity of magnetization is the extent to which a specimen can get magnetized. It's specimen related. A copper வைக்கிற silver வைக்கிற, depending on what metal you are keeping, it has its own magnetizing ability. So that's specimen related. If you write like this, extent to which a specimen can get magnetized, they won't give you marks. You also should write moment acquired per unit volume. Very good. Moment acquired per unit volume, and write the same as unit ampere per meter, because both of them refers to anyway magnetizing ability, whether its own ability or field's ability. So susceptibility is I by H. Susceptibility as a word, you can see that the meaning of it is the extent to which a substance can get magnetized. So is the ratio of intensity of magnetization to magnetizing field intensity. I am supposed to write I like this, or I have to refer it as M like that. You can either write it as I or M like that. It's your wish. However your teachers are referring to, you can refer it. But I prefer I by H because I sneezed and I taught you I by susceptibility. So this from this we are going to write the total magnetization in a medium is BH plus BI, which is mu naught into H plus mu naught into I, which will be mu into H by the first equation. So you know you can divide throughout by H. Dividing throughout by H, this will become mu is equal to mu naught plus I by H, which so mu naught into I by H, and I by H itself is susceptibility. Mu is equal to mu naught plus mu naught into susceptibility. Mu is equal to mu naught can be taken out 1 plus susceptibility. So mu by mu naught is equal to 1 plus susceptibility. This itself is mu R is equal to 1 plus, and whenever I tell you this formula, you are kind of stuck. Mu R is mu by mu naught, you should know that. Relative permeability is always permittivity of the medium by permittivity in vacuum. And with that only I am writing this. So you should know this. Next, after this, I taught you the difference between dia, para and ferro. So let's deal with this. This is dia, para and ferromagnetic substance. First is you're going to suspend a diamagnetic. You're going to suspend. This is the magnetic field. When you're suspending, I'm just drawing a thread here to show it's suspended. It's coming to rest in perpendicular to the magnetic field. Whereas a paramagnetic specimen, when you suspend it, will come to rest in the same direction as the magnetic field. Ferro is also the same. And then you're going to place it. When you're placing a diamagnetic specimen in a uniform magnetic field, the magnetic field is getting expelled when you place a diamagnetic specimen. When you place a paramagnetic specimen, the magnetic field is getting contracted. Okay, so whereas when you keep a ferromagnetic, contraction, so many field lines are passing through. Okay, this is what it is when it is placed. Under the place, there's also one more point. Diamagnetic get weakly magnetized in the opposite direction. Weakly magnetized in opposite direction. This gets weakly magnetized in same direction. This gets strongly magnetized in same direction. The difference between this, why is it, I'll explain to you later as we progress. Okay, next is this is when placed a diamagnetic specimen. Remember Diana, she moved from a stronger position to weaker position. Take a diamagnetic specimen, molten diamagnetic specimen, molten, so that it can move. Okay, so you place it between North Pole and South Pole. You know, near the poles it's strong field, away is a weak field. She moved from stronger to weaker. Diamagnetic moves from stronger to weaker. You move the magnet away. Here it will be stronger, but center it will be weak. So she will move to weaker side, no? Diamagnetic. Paramagnetic, when you draw the same diagram, here is where stronger is there. She moves from stronger to weaker, closer. Here it's paramagnetic moves from weaker to stronger. And the ditto for this, when you move it away, it should be, because you moved from weaker to stronger. Near the poles is strong. The same thing ditto for ferromagnetic. Okay. The next thing, this is about Diana. She didn't obey the rules of the palace. So then this won't obey Curie's law. What is Curie's law? Susceptibility versus temperature has to be inversely proportional. Susceptibility is inversely proportional to temperature. Is what is Curie's law. Correct? And paramagnetic is obeying that, but diamagnetic is not obeying. But ferromagnetic obey Curie-Weiss law. what is Curie-based law is, he says susceptibility is inversely proportional to T minus Tc, where Tc is the Curie temperature. At lower temperature, there's a temperature called Tc above which it will obey, but below which it will not obey Curie's law. It's only obeying Curie-based law, where it's becoming infinity. The susceptibility is becoming infinity and behaves like permanent magnet, which I'll explain later. So let's memorize this graph. Okay, so next is difference is about paramagnetic is basically unpaired electrons. Para is where the unpaired electrons are. Okay, before which I'll talk about susceptibility. Susceptibility is slightly negative. Susceptibility is slightly positive. And susceptibility is largely positive. So relative permeability is slightly less than 1. Slightly less than 1. And relative permeability is slightly greater than 1. And this is much greater than 1. When they say 2000 and all to be the relative permeability, it refers to ferromagnetic substances. Say 1.2, 1.02 and all, it's paramagnetic. And 0.8 and all is diamagnetic. So like that you should write. And then as about paramagnetic has got unpaired electrons. Whereas here it's got completely paired electrons in dia. So this has got a natural dipole moment. This has got a natural dipole moment. And this also is the same. Ferro also same as para. Okay, so these are the points and examples you should remember. Diamagnetic, anything that is glittery, such as zinc, gold, and also silver. And bismuth, very important is bismuth is very important example. Nitrogen is actually, you will think nitrogen is unpaired. No, nitrogen exists as N2, so it is also paired. And water and copper 1 plus. Similarly, you have copper 2 plus here, and you must ask your teacher when they say ask copper it's 2 plus or 1 plus, you tell me, then only you can write the answer. Correct? And then anything which ends M, such as platinum, aluminium, calcium, magnesium are all examples of paramagnetic substance. Ferromagnetic substance is iron, cobalt and nickel in general. Cobalt and nickel, and I will go through this further later. So these are the examples you should say. So next thing that I want to teach you. Okay, in ferromagnetic itself there are 2 categories. Okay, in ferromagnetic itself it's classified into a soft ferromagnetic substance and hard ferromagnetic substance. Iron, cobalt and nickel are called soft ferromagnetic. Hard ferromagnetic substance are alnico, aluminum, nickel and cobalt alloy. And then lodestone, Lodestone, steel, they are all hard ferromagnetic substance. And this lodestone is what is compass box made of. You must have lifted the compass box, it will be very heavy. The lodestone is made up of, it's a compass box made up of lodestone. Jurassic Park, நம்ம தான் வந்து ஏதோ அமேசான் காட்டுக்கு போகிறோம், ஒரு பெரிய திமிங்கிலமோ என்னமோ நம்மக்கிட்டேருந்து அந்த இது வாங்கிடுது காம்பஸ் நீடில். நம்ம அதை பார்த்து தான் காட்டிலேருந்து வெளியே வந்துட்டுருப்போம். அது போட்டு டப்புன்னு அடித்து உடச்சா கூட it will still have its magnetic effect. Okay, that's why it's made up of hard ferromagnetic substance. Then I'll explain why a paramagnetic and a ferromagnetic, this is weakly magnetized in the same direction, whereas this is strongly magnetized in the same direction. I'll explain பண்ண போறேன். For this explanation, I will tell you the diagram given in the book. They will divide it into different domains. Okay, in paramagnetic, let's divide it into different domains. Each domain has about 10 to the power 15 atoms. And alignment, paramagnetic has got unpaired electron, they have a dipole moment. The alignment is the one in like this, one is like this, one is like this. Different alignments are there. So the net magnetic field is reduced. That's why it's getting weakly magnetized. In the case of ferromagnetic substance, when you break it down into different domains, you have the magnetic field all aligned well already, and so then they produce a stronger magnetic field. Okay, but the thing is, in the textbook they've also given gadolinium. Gadolinium is an example of soft ferromagnetic iron, cobalt, nickel are categories as and the relative permeability is greater than 1000 for this. Okay, and they termed as soft ferromagnetic substance. That's all. They didn't mention anything more. So you know that the ferromagnetic substance basically has greater than 1000 as the relative what is it, relative permeability mu r, correct? And then what else did I miss? I have to write what is Curie's law. So let's write what is Curie's law. Curie's law states that Curie, no scientist, states that susceptibility is inversely proportional to temperature, and this was applicable only for paramagnetic. For ferromagnetic, it was obeying it obeyed Curie's law only for higher temperature. Ferromagnetic substance obeyed Curie's law only for higher temperature. Therefore, there's a temperature called Curie temperature, below which it was doing differently, and this is called Curie-Weiss law, and this was found by Curie-Weiss. He improved the Curie's law and wrote Curie-Weiss law, and he said that a ferromagnetic substance obey Curie-Weiss law, and in this its susceptibility versus temperature is inversely proportional. Here there's a critical temperature. So this is like it's inversely proportional temperature. When the temperature is becoming lesser, susceptibility is becoming infinity only for ferromagnetic. And then it's like this, which is as usual like this. For higher temperature, the same. Lower the temperature, what is happening in ferromagnetic substance? When you lower the temperature, the thermal agitation gets reduced. Thermal agitation gets reduced, because of which the susceptibility is increasing. That too increasing till infinity. Imagine, no, when the temperature is 0. Susceptibility is becoming infinity, and not exactly like that. This is Tc and this is T. When the temperature approaches Tc itself, it is going to infinity. It's not even coming to 0. We're not even talking about 0 here. When the in the case when the temperature is coming closer to Tc, Curie temperature itself, the susceptibility base is becoming infinity, which means the ferromagnetic substance has an immense ability to get magnetized and behaves like a permanent magnet at lower temperature. Permanent magnet at lower temperature. Something so beautiful. You have got to remember this. Next is Gauss law in magnetism. Gauss law in magnetism. It states that B dot ds is equal to 0. Surface integral of magnetic field over a closed surface is always 0. Why? Why? Because monopole does not exist. Monopole does not exist. You can't have only a north pole. It will always have a south pole, and the net field will be 0. No, don't say that. You can't have a unit north pole. That's all, because magnetic field is mu naught by 4 pi into m by r cube, r square or whatever, r square. But m is the monopole. Okay. A monopole cannot exist. In a closed surface, monopole cannot exist. You place a magnet, it exists as a dipole only, no? Correct. It comes along with it. So monopole does not exist, and therefore the magnetic field B dot ds becomes 0. That's about Gauss law in magnetism. Next, what should I say? Next, what should I teach you? Next, I'll teach you what is a hysteresis loop. Hysteresis loop. Okay, you must have studied this last year when you stretch a rubber band. It goes like that, and then it doesn't take the exact path because some amount of energy is lost in the form of heat. So ஒரு rubber band stretch பண்ணா release பண்ணப்பறம் அதோட original stretch இருக்காது. It will not come back to its own position. Stretched ஆயிடும், கொஞ்சம் stretch ஆயிடும், அதனால some energy loss இருக்கும். Okay. So இப்போ இதை வச்சு பண்ணுறோம் hysteresis loop. So let's draw this diagram. I hope it's recording. Yeah. So hysteresis loopல you have a H versus M. Mங்கிறது M கிடையாது, நம்மளை பொறுத்திருக்க அந்த I, intensity of magnetization, or this M, whichever you can call it. Okay. So the I versus H, I by H will give you susceptibility, no? So that's graph you're going to do. You have to memorize this graph. It goes like this. Okay, it touches the axis like this, then goes like this and goes like that, and then when it comes back, it comes like this and comes like this and comes like this. This is the hysteresis loop. Okay, where you see that so I'll explain this. In this, if you see, we are magnetizing and demagnetizing. Or substance, you are magnetizing it and removing it from the magnetic field. It gets magnetized and demagnetized. A rubber band gets stretched and de-stretched. Correct? Like that, you're magnetizing and demagnetizing. Abhi பண்ணிட்டே இருந்தா it will lose energy. Correct? அது rubber band மாதிரி தான். So this is for initial magnetization. This is magnetizing, and this is the path when taken when demagnetizing. Okay, the path for magnetizing and demagnetizing are just not the same, because there's some amount of loss of energy in the form of heat or whatever. So in this, if you see, while at 0, when H is 0, you still have a residual I, which is specimen related, right? This is specimen related I, and it's still having an I value. Even though H has become 0, you still have a residual I value, and this is called residual magnetism, Br. Even though H is becoming 0, that is when you magnetize and then you demagnetize. When H becomes 0, you expect I also to become 0, but H is becoming 0, but I is not becoming 0, which means even when you demagnetizing, even though the field has become 0, but I is still having residual magnetism, that's called Br. Are you clear? This point C is what is called residual magnetism. Okay, and that's all. And you know that this is occurring because of loss of energy. And I wish I can tell you more information. Hysteresis with coercive field. Coercivity and those details. Understand that this is residual magnetism. Still some magnetism is left, even though H has become 0, and that's called retentivity. So what is retentivity? When you magnetize and demagnetize, even though H has become 0, the magnetism is still there, B is still there, and that's called retentivity, retaining. And this point, let's call this point as they call this point as B. Let's call this point as C, and this point C is called coercivity. At which you see the H is becoming negative, and the magnetism, or what is it? Specimen's magnetic field is becoming 0. That's what is coercivity.
Reversed an external field applied to completely demagnetize.
So this is the point when it's getting completely demagnetized. It's losing complete magnet. I is becoming 0. And at which point H is becoming a negative value. That is the point of demagnetization of the substance, when you reverse the field. So this whole thing is about magnetizing and then demagnetizing. When you demagnetize, you are left with the residual magnetism, which is called retentivity, and in order to remove that, you have to further reduce the field magnetism to some negative value, so that the retentivity becomes completely lost, and the magnet at that point is called coercivity. I hope you're clear. So now some left out points. So you understood what is retentivity, what is coercivity, and then you also know there is this area under this loop gives you energy, loss of energy per unit volume. Loss of energy per unit volume, which is area under this graph. Suppose let's call this as dA. Area, what is this area under the loop? Is dCBA minus, let's call this as E, minus area under DEA. This upper area minus lower area, which you normally do it by integration, you will get the area of the graph, which is loss of energy per unit volume. Next thing that they are talking about is they are saying a soft ferromagnetic substance has got small hysteresis loop, and a hard ferromagnetic substance has got large hysteresis loop. That's something that I didn't teach you. See, suppose then between iron and steel, you know that iron is a hard ferromagnetic substance. Steel is a hard ferromagnetic substance. Iron is a soft ferromagnetic substance. For a soft substance, the small energy, loss of energy is less. The hysteresis loop will be very narrow. Whereas for a hard ferromagnetic substance, there's a large hysteresis loop.
More energy
loss. So that's something you need to understand. For iron, loss is very very less. Similarly, for a hard ferromagnetic substance, retentivity is also large. Okay, so which means for this we should draw the graph in such a way that the retentivity is more. Are you clear? Much more than this. Can you see the retentivity point is much more? For a hard ferromagnetic substance has got large retentivity. Yeah, obviously permanent magneட்டாவும் இருக்க போறதில்ல அதனால கரெக்ட்டா. And also large coercivity. The coercivity should also be large. Make sure that the coercivity point is also much larger. So large coercivity. Okay, then this hard ferromagnetic substance, since there's a loss of energy is much more, you can't be continuously magnetizing and demagnetizing. It's difficult to magnetize and demagnetize, whereas this is easier to magnetize and demagnetize. The process becomes easy. So this is soft iron is an example, and you know it's got a narrow hysteresis loop. Then they seem to have also done this derivation. You know, magnetic moment of a bar magnet. I taught you magnetic moment of a solenoid and of revolving electron, sorry. Of a revolving electron. Now they're going to talk about magnetic moment, which is m into 2l. Okay, and you're going to cut this into n parts. I don't know, whatever this question is, it's been cut into n parts. Okay, so if you're cutting it into n parts, the magnetic moment remains the same, but the L becomes L by n. Each of the L pieces, each of these pieces becomes L by n, correct? And you know the total length itself is 2L.
Yeah.
So 2L by n is what they're saying. They're not saying it as L by n. That's another point that you should mention. So you know that nu m dash for one such piece is the magnetic moment remains the same, correct? But the length becomes 2L by n. So so this is the new formula we get. And you know m into 2L itself is capital M, magnetic moment vector, by n. So that is what is a new m dashes. So m dash get divided by n.
Okay.
The original moment gets divided by n numbers. So you know that okay, we'll keep it till here. Then they are also finding what is I dash m by n. They're finding what is m by n. One second, hold on. Generally, you should know the time period of time period of oscillation for a bar magnet. The formula is 2 pi into root of moment of inertia by mb. This formula is from last year's syllabus. 2 pi into root of L by G for a pendulum. But when it comes to bar magnet, you will have moment of inertia. It's going to be oscillating like this and like this. So it's I by mb. This is the formula you need to know. And you know what is m for the cut piece. And you can also find the moment of inertia of a cut piece and magnetic field. I think that's what they have done. One second, let me just check that. So let's see this, okay. You know that the new piece has got length, which we are taking it as 2L by n. Here they taken it as L by n. We have taken it as 2L by n because for us the length of the magnet is 2L, correct? So, but in internet they seem to have taken it as L by n, but that's okay. You just note this as the first one. Then the new moment, let's calculate the new moment. M dash, we have calculated it. It is capital M by n. Yes, this is the second observation because we need to substitute it. You need also moment of inertia. How to find the moment of inertia of the cut piece, I dash? It is initial moment of inertia by n cube. Initial moment of inertia by n cube. Since I is proportional to m, moment of inertia is proportional to mr square. So mr square, which is m into length square. Length is inversely proportional to n square. Already length is inversely proportional to n only. No, here n square. How is it n square? You know the L is already inversely proportional to n, inversely proportional to n, so it becomes n cube. Okay, let's see. Moment of inertia is inversely proportional to the new moment of inertia is I by n cube, where moment of inertia is m into L square. Okay, the mass the mass is got divided by n because you've cut into n pieces. So already new mass is inversely proportional to n.
Okay.
Okay, length length is inversely proportional to n square. So n square and n together will make it n cube. So you don't have to know, just memorize this. The moment of inertia, new moment of inertia is original moment of inertia by n cube. If you know this, then you can substitute the formula T is equal to 2 pi into root of, what is the new moment of inertia? Old moment of inertia by n cube by capital M. Capital M, we calculate with capital M, which is capital M by M dash, which is capital M by N. So we have a capital M by N into magnetic field remains the same, N and N square item. Correct? It's 2 pi into root of I by N square MB. I by MB, root of I by MB, 2 pi is the original time period. So it's dividing by 1 by N times the original. The new time period is original time period divided by N. Let me explain to you once again. So take a bar magnet. What will be the time period of this bar magnet? You should know 2 pi into root of moment of inertia by MB according to last year. Now you are cutting the whole magnet of length n times, which means moment remains the same, but the length is becoming 2L by N according to us. For the net it is L by N. So net, okay. And a new magnetic moment is the pole strength remains the same, but the length is becoming 2L by small n, which itself is capital M by N. So right, this is the new moment. Okay, you want to find the new inertia. New inertia is old inertia by N cube. Just write this. Okay, new inertia is this, and magnetic field remains the same. So new time period is 2 pi into root of I dash by M dash into B. 2 pi into what is I dash? I by N cube. What is M dash? Continue. What is M dash? Is M by N. And write B. N and N square. It becomes 2 pi into root of I by N square into MB. The original time period is this. So you take it out. 1 by N times the time period initially is the T dash. So this is the formula. Okay, that's what it is given in your book. And you understood coercivity, retentivity and all. So generally we say that in hysteresis loop, the hard ferromagnetic substance has got high coercivity and high retentivity. But that doesn't apply for every metal. It can vary from metal to metal. So let's talk about soft iron for that matter. Okay, soft iron has got definitely high retentivity, but it's got low coercivity. Slight variation. High retentivity, in general, soft iron is actually a soft ferromagnetic substance, which should have low retentivity and low coercivity.
Correct.
But actually speaking, soft iron seem to be having high retentivity but low coercivity. That's a special nature of soft iron. You cannot categorize, it is a soft ferromagnetic substance, however, its behavior is peculiar, and soft iron is the only metal which we can use it as a permanent magnet also, because of its high retentivity nature, but low coercivity. Are you clear? Next is next alongside alloys like alnico also. Soft iron is has got high retentivity, low coercivity. Whereas alongside special alnico, okay, they are saying retentivity of soft iron is 1 Tesla to 1.2 Tesla. Steel has got lower retentivity and higher coercivity. Oh, steel has got lower retentivity? We thought steel is a hard ferromagnetic substance, it's got high retentivity, but that's not applied here. It's all very varied. So you see that steel has got low retentivity and high coercivity. So this is something that is peculiar in nature, and you need to memorize this, know that. So which means whatever we said it there in the hysteresis loop is just a general statement. It may not be true for everything. You seem to be, here is a soft iron which has got high retentivity, low coercivity. Here is the steel which is a hard ferromagnetic substance which has got low retentivity and high coercivity, is something that you need to memorize. Okay, so that's enough, guys. Let's not do more. And so I'm going to do, is it recording? Yeah, some numericals which was given in my PDF. You can refer to my PDF. Okay, the first question. You have a bar magnet whose length is given as 10. So don't take L is equal to 10 centimeter. Even though length is 10, it's 2L is equal to 10. Because this side there's an L, this side is in, there's a 2L. Okay, and the pole strength means small m, is 10 ampere meter. Small m has been given. Calculate the magnetic field at a distance 0.2 meter from the center along an axial line. So it's R is equal to 0.2 from the center. What is L? L itself is actually 5. Along an axial line, what's the formula? B axial is mu naught by 4 pi into 2m r by r square minus L square the whole square. Here you can't ignore L. It's given, L is given. And it's centimeter, L is 10 centimeter means 0.05 meters. So substitute that, this itself is 10 to the power minus 7. And 2 into capital M. What is capital M? Is either of the pole strength into 2L. The pole strength is given to be 10. The 2L is given to be 10. So substitute here 10 into 10 into position vector 0.2. R itself is 0.2 by R square minus L square the whole square. And write the answer in terms of Tesla. You get the answer. That's third. And the same question they've asked for equatorial line. If they ask you for equatorial line, say the same question at a point P which is at this distance, you can apply 0 mu naught by, you don't have to find it. You know that B axial is 2 times B equatorial. So B equatorial, half of this, you divide this entire answer by 2 and write it as B equatorial. So easy. So let's go to next question. So next question is this. Two small magnets are placed horizontally perpendicular to the magnetic meridian. So let's consider this to be the magnetic meridian. So this is the magnetic meridian. Now I'm going to place a magnet perpendicular to the magnetic meridian, means I'm going to add that to the east and to the west. The north pole of one magnet is 30 centimeter east. And the north pole of another magnet is 20 centimeter towards the west. So this is 30 degree east and east park 30 degree 30 centimeter 20 centimeter west. Now they are saying that if the compass needle is getting undeflected at this point, which means the net magnetic field is becoming 0 at this point, which means this is along axial line of both these dipoles. Axial line will be like this. This will be B1, which is because of the first magnet, and there will be a B2, which is due to the second magnet. Correct? Axial line, and they have not given the length of the magnet here. So which means R is much larger than L. We can take it like that. So and find the question is to find the net magnetic field and equate it to 0. So what is the red color magnetic field? It is due to left magnet, but you can ignore the length. You can ignore the length. The small L can be ignored because they have not given the L in the sum.
Okay.
So it's mu naught by 4 pi into what is axial in formula? 2m by r square minus L square into r whole square. But in this, L can completely get ignored. So the formula will be mu naught by 4 pi into 2m by r cube. And capital M is small m into 2L. Again, this 2L can be ignored. We're keeping them as unity. So it is only m. Let's write it as small m1.
Okay.
Which can be equated to the green color's axial line, which is second bar magnet's axial line, which is mu naught by 4 pi into 2m2 by r cube. This is r1 cube, this is r2 cube. One is 30, another is 20. Correct? So write 20 cube here and 30 cube here, whatever it is, and or 30 cube here or 20 cube here, and then cancel off the mu naught by 4 pi, mu naught by 4 pi, 2 and 2 get cancelled. Thus you can find the ratios of m2 by m1 is 30 cube by 20 cube. Is it? Okay. So this is
8 by 27.
3 3s are 9, zeros and all will get cancelled. 3 3s are 9, 3 is 27, 2 2s are 4, 4 2s are 8. So m1 by m2 is in the ratio 8 is to 27. So you have to understand this point is axial line of this bar magnet and axial line of this magnet, and they both are acting in the opposite direction and cancelling out. Obviously,
Yeah.
Because North Pole only should point away from the north. So that's the first question. Next question that I did in my PDF, which are there in Aurora, is two bar magnets P and Q are placed one over the other perpendicular to each other. They're calling this bar magnet as P and this as Q. And they're saying that it is found that the resultant at a point on the prolongation of the magnetic axis of P. The magnetic axis of P is getting prolongated. And at some point A, the resultant R, the resultant is making an angle 30 degree with the horizontal. Appadina, there should have been a magnetic field B1 which is like this. There should have been a magnetic field B2 like this. The B2 happens to be the equatorial of this.
Okay.
And B1 happens to be the axial of this. Do you understand that?
Yes.
Yesterday when I was explaining that, you were struggling to understand. So you should understand this is... So now what is... Let's write the red color's magnetic field. What is red color? It's axial, right?
Yes.
Which is based on this magnet. Which is... Again, the length of the magnet have not been given. So capital M can be written as small m 1 into 2L. So you're considering if this is M1 and M2. Okay, so this will be mu naught by 4 pi into 2 M1 by R cube B1. Correct? And this is equatorial, which will be, what will be the value? Mu naught by, this will be B2, which is mu naught by 4 pi into 2 M2 by, no 2, M2 by R cube. Because equatorial doesn't have a 2. So you know that the resultant, if you want to find the resultant magnetic field, it's root of B1 square plus B2 square. So you can take this B1 square, mu naught by 4 pi 2 M1 by R cube the whole square. But the distance R is just the same. And L we have ignored. Because equatorial axial R is just the same in both cases. So plus mu naught by 4 pi into 2 M2 by R cube the whole square. Whole square. So what's common here? There's no 2 here, no? M2. There's only M2. There's no 2 because equatorial. What is common here? Mu naught is common. 4 pi M1 R cube. So what you have is a root 2 plus 1 within square root of this will become 4, is it? Whole square, no? 2 2s are 4 plus 1, right? Because this is whole square. So it will become 4 plus 1, it will be root 5. Okay, you understand, that's the value. Then they'll ask you for tan 30. What is tan 30? Tan 30 is 1 by root 3, which is opposite by adjacent, which is beta 2, B2 by B1. You know the value of B2, and you know B2 is equatorial, so it's 1 by 2, no? The magnetic field is 1:2 ratio. So 1 by root 3 is to 1 by 2B.
So, okay, this is the
B by 2. This is B and this is 2B. Correct? B and B get cancelled. What am I supposed to write? What is the question? Magnetic moment. Oh, you have to write in terms of small m1 and this is m2 and this will be m1 and you'll have a 2 here. The 2 will go to the other side. So m2 by m1 is 2 by root 3. Yeah. And that's the answer. They'll ask you for the ratio of the pole strengths. Ratios of the pole strengths. Or the ratios of the magnetic moment also will be the same because we've taken L to be the one unity. So if they ask capital M1 by M2 also will be in the same ratio. Are you clear?
Yes.
So next question that we have done in the PDF is this. Two identical magnets, dipole of magnetic moment, ampere meter square. So capital M has been given. Okay, each are placed at the separation of 2 meter. One is placed like this, another is placed like this. Such a way the distance is 2 meter. And exactly midway, which means this side is 1 meter, this side is 1 meter. We are trying to find the magnetic field. So this will be the axial line because this is north pole, south pole. This will be the axial line. It's called this as B1.
Yes.
Due to this magnet. For this magnet, it will be equatorial line. And if this is north, this is south, you know it will be from north to south. This will be B2. And you can find the resultant of this, which will get you the resultant magnetic field, which is root of, this is B is equal to root of B1 square plus B2 square. And what is this? Here again, they didn't give you the length of the bar magnet. So we can take it to be negligible or unity.
Okay.
Okay, L is, you can ignore L and you can treat this as consisting of M1 and pole strength M2. Each of the bar magnet has pole strength M1 and M2, just like previous sums, okay? So what is the axial line formula? B1 is this green color and axial lines formula is mu naught by 4 pi into 2 M1 by R cube is 1 cube, no?
Okay,
Because we are ignoring the L also. And what about the red color magnetic field is equatorial line formula, which is mu naught by 4 pi into M2 by R cube again is 1. And you want to find the resultant B is equal to root of B1 square plus B2 square, which is mu naught by 4 pi into 2M1 the whole square plus mu naught by 4 pi into M2 the whole square. From this what's common? Mu naught by 4 pi into M. This is M1. Can we call it as M and M? The pole strength have they given identical magnetic dipoles, which means M1 is equal to M2 is equal to M. In that case, they didn't ask for ratios of the magnetic dipole moment in this sum, so you can take it as M.
Okay.
And so what you have here is a root 4 plus 1 again, which is becoming a root 5, and then that you get the resultant. And what else they are asking? That's all. You know, it's small m, right? If they give you the small m, they've given small m to be small m. They didn't give but capital M is small m into 2L. We are taking this as unity. So small m is equal to capital M. You can always plug in this value of 1 here. So you get mu naught by 4 pi into root 5. Okay. This itself is 10 to the power minus 7. 4 pi get cancelled. Root 5 into 10 to the power minus 7 Tesla is the final answer. Okay. And supposing they ask you the angle theta. You know tan theta is B2 by B1. Which will always be equatorial and axial distance is the same. It will be 1:2. And where will tan theta be 1/2? You don't know. But theta is tan inverse of 1/2.
Yeah.
Just leave it like that. Okay. So then theta therefore is tan inverse. Next question is some 12th question. A magnetic needle of magnetic moment 4.8 into 10 to the power minus 2 joule per Tesla. I told you it can be ampere per meter square or joule per Tesla is capital M. Is placed at an angle 30 degree with the direction of the uniform magnetic field, which means you should know one thing. When you have a bar magnet, the magnetic dipole moment is always from south to north. The direction of the moment is always from south to north. Are you clear? So this is going to be placed in making an angle 30 degree with the uniform magnetic field. You understand?
Okay.
So they are asking for torque. Torque is equal to MB sin 30. What is magnetic moment itself is given 4.8 into 10 to the power minus 2. Magnetic field strength is given to be in this question uniform magnetic field 3 into 10 to the power minus 2 Tesla and sin 30. What is sin 30 is 1/2. Just find the answer, right? That Newton meter is force into perpendicular distance. So Newton meter should be the SI unit. So let's go to next question. A short bar magnet of magnetic moment 0.9 joule per Tesla is undergoing a torque of 0.063 joules. Torque has been given. You know, torque is equal to MV sin theta. They have given theta in the sum as 30 degree.
Sin 30.
And you can find B because you know torque which can go here. You can, you know, magnetic moment which can be plugged in here. With this you can find what is B and write the answer in terms of Tesla. Are you clear? Yes. Then a most common question which comes in every paper in this lesson is you have a circular, they'll give you a circular coil and a current will be passing through this coil like this. When the current goes like this, according to right hand thumb rule, keep the thumb in this direction. The curled finger hugs and goes like this. So outside to inside, outside to inside. Like this, keep the thumb in this direction. It goes like this, outside to there inside, outside to inside. So you have a magnetic field which goes from bottom to top. Make sure there are no lines crossing each other. So this is like a south pole and the north pole of a magnet. A coil itself behaves like a bar magnet. Similarly, a solenoid also will behave like a bar magnet. A solenoid and bar behaves exactly like a bar magnet with a north pole here and a south pole here and a uniform magnetic field. So if they ask you to draw the magnetic field of a solenoid, just treat it, imagine this to be north pole and this south pole. Outside the bar magnet goes from south to north. Outside the bar magnet goes from south to north. Within the bar magnet goes from, what am I saying? North to south outside the bar magnet. Within the bar magnet goes from south to north. I'm tired. Okay, and goes like this, and therefore it's exactly the same lines as a bar magnet. Can you see?
Yes.
And therefore, we can say that the solenoid exactly behaves like a bar magnet. The most important thing I would like you to say is in a solenoid, when you know it's behaving like a bar magnet, if the magnetic field at the center is B, the magnetic field at the edge is B by 2. Why? Because the magnetic field line is actually spreading away there. The field lines is moving away there. So then therefore we say the magnetic field at the center is not the same as magnetic field at the edge, because solenoid is a huge one. It'll be really long solenoid. So the magnetic field at the center is not the same as magnetic field at the edge. At the center the value is mu naught into small n into I. I always recall this from the last lesson. I call this as quarter formula because this is small n. I say quarter formula mu naught into small n into I. Okay, so that's about this. Let's go to next question. Next question is in a hydrogen atom, some 16 sum, an electron moves in an orbit of radius 0.5 Armstrong and making 10 revolutions per second. It's making 10 revolutions per second, which means this is the frequency. If you know mu, you can find omega. Omega is 2 pi mu, so it's 20 pi radians per second. Okay, why? Because they are asking for magnetic moment. I know the formula QVR by 2. And I know linear velocity is r times angular velocity. So I have to multiply this 20 pi with the radius, which is 0.5 into 10 to the power minus 10. That will give me my V. So I know V. I know R, 0.5 into 10 to the power minus 10 meters. I know charge of an electron is 1.6 into 10 to the power minus 19. Substitute all the value, get the magnetic moment. Write it as Joule per Tesla or ampere per meter square. Your wish. Are you clear?
Yes.
And next question is an electron moves around a nucleus of a hydrogen atom with radius 0.151 Armstrong, which is 0.51 into 10 to the power minus 10 meters. Correct? Radius has been given. They have given the velocity. Velocity with which it's rotating is 10 to the power 6 meter, 2 in 10 to the power 6. Then they are asking magnetic moment. It's QVR by 2. No, you know V, you know R, you know the charge divided by 2. You get direct answer. Yes, it's either Joule per Tesla or ampere per meter. Ampere per meter square. You're right. So let's go to next term. In this sum, they're asking what is the current. I is equal to Q by T. Q is the charge of an electron 1.6 in 10 to the power minus 19. Correct? Minus 19. Charge of an electron. Time is time period, which is 2 pi r by v.
Okay.
So you know the radius, you know the velocity. If you don't substitute you understand t as 2 pi r by v. You won't get the answer otherwise. I is equal to q by t. Correct?
Yeah.
Q is charge of an electron. T is the time period, which is 2 pi r by v. So if you then you know what is velocity, then you know what is radius, you know the charge. You can find the current and write the answer in ampere. Then they are asking for what is the magnetic field at the center when the electron is revolving. It's making a circular loop. The magnetic field at the center is mu naught by 2 into I by A or I by R radius according to last lesson. Okay. This is according to last lesson. Circular coil, the magnetic field at the center is mu naught by 2 into current carrying circular coil. When an electron is revolving, it's like current carrying coil mari irukku. So then you treat it as the previous lesson, mu naught by 2 into I by R. You know what is I? We have found I. You know the radius. Substitute. What is mu naught? Mu naught is 4 pi into 10 to the power minus 7. Correct? You can check my PDF and complete it. These are all Aurora sums. So I'm just giving you a hint of how to complete every sum. The third part of the question is they are asking for magnetic moment. It's normally near, but here n can be taken as, you know I and you know pi r square is the area. With that you can get this answer. Magnetic moment ampere per meter square. Let's go to next question. The next question is a bar magnet of magnetic moment 2.5 joule per Tesla lies along the direction of uniform magnetic field 0.32 Tesla is lying along the direction, means the bar magnet and this are parallel to each other. When theta is equal to 0, which means theta is equal to 0. Torque is mb sin theta. No, the magnetic moment also is in this direction. Yeah, which is from south to north, and the external field is also in the same direction. Okay. Theta is equal to 0. Now they are asking you to rotate this magnet by an angle of, align it at a perpendicular to the magnetic field. From this direction, you're going to align it in this direction, which means from theta is equal to 0, you're moving it to theta is equal to 90. So you should use the derivation formula where potential energy, you got it as minus mb cos theta 2 minus cos theta 1, where theta 1 is cos 0. Cos 0 is 1. And this is cos 90. Cos 90 is 0. Minus and minus 1 will get cancelled. Potential energy will be plus mb. That is the energy required to rotate it from this alignment to this alignment. The next question is, when from this alignment, where it's parallel, you have to align it to anti-parallel. Here is south and here is north. So from 0 degree to 180 degree you're going to move. Yeah, in the same formula you can write u is equal to minus mb cos theta 2 is 180 and cos 0 is initial. Cos 0 is 1 and this is minus 1. Minus 1 is minus 2 to become plus mb. That is the total potential energy, 2m. Because minus 1 is minus 2. Minus 2 into minus 1 is plus 2 mb. So therefore you get the potential energy required to rotate it like this. They might ask you any question like rotate it through 40 degree, 45 degree, whatever.
Okay.
You should know initial angle and final angle. I can substitute this. So let's go to next question. Next question is, in the PDF I would have written PE by mistake. In electrostatics it's the electric dipole moment. Here it is MB. So please correct it. Okay. So let's go to next question, where they have given
A current of 2.
a current of 7 amps
7 ampere.
is flowing through a circular coil of radius 10
1
centimeter. 1 centimeter is it? 1 centimeter, which is 0.01 meter. Okay.
Having 100 turns.
This is called n turns. N is equal to 100. Okay, I can call capital N also 100 because they just specified total turns. They didn't say per length.
So we don't have to use more.
You can 100 turns. The coil is placed in uniform magnetic field is 0.2 Tesla Weber per meter square. It can be written as Tesla. If the coil is free to rotate, what orientation would be for stable and unstable?
Okay.
You know that theta is equal to 0 stands for stable and theta is equal to 180 stands for unstable. For what orientation? You just write potential energy is minus mb
That is
cos 0, and this is minimum potential energy. This is maximum potential is plus mb cos and minus mb cos 180, which will become plus mb.
Okay.
And in this m is actually for number of turns of the coil Nia.
Oh.
And b is mu naught by 2 into I by a at the center of the circular coil.
Okay.
So you should write mu naught by 2 into, have they given the magnetic field? Then there is no problem.
That's a
So that's external magnetic field, sorry. So you can substitute this value here. But M is given by Nia.
Yeah.
Number of turns is 100, I is the current 7 amps, A is pi r square.
All the
And just plug in this value and get those values and write it. That's what makes this some difficult. So let's go to next question. You can check my PDF if you want more details. So let's go to next question. Is a solenoid. And this is a book sum that I taught you. Now I'm going to teach you that once again. There is a book sum which we did, and I'll do it once again for you all. Where this is in page number 146. Okay, a solenoid has a core. It may be iron or something with relative permeability mu r is equal to 400. So they've given mu r of the medium inside the solenoid to be 400. The windings of the solenoid are insulated from the core and carry a current of 2 amps. So you know the current that's passing through the solenoid is 2 amps. The number of turns is 1000 per meter. When they give 1000, number of turns is capital N. But they've given per meter, so it's small n. So you know small n is 1000. And then they're asking to find what is H, what is I, what is B, what is IM. For me, the textbook says M, which is intensity of magnetization, can be called as M and also called as I. To differentiate it from current and magnetic moment, I'm writing it differently. Okay. So you can either call it like this. They're asking for H. I know the definition says ampere turns per unit length. So ampere turns per unit length is 1000. Ampere is the current, which is 2 amps. So 2 into 1000. I directly get 2000 ampere per meter to be the magnetic field intensity H. Immediately I get the answer. If I know the definition only, I can write quick answers. Don't see the textbook for answers. I've got easier ways of solving it. What is I? To find I, you know susceptibility is I by H. You know H, you know relative permeability is 1 plus susceptibility. This has been given in the question as 400 is equal to 1 plus susceptibility. Therefore, susceptibility is 399. Let's approximately take it as 400 for make the calculation easier. So, you know 400 is equal to I by H. What is H? 2000. Therefore, I is 4 2s are 8 into 10 to the power 1, 2, 3, 4, 5. 10 to the power 5 ampere per meter. Now, I found that. Now, to find B. To find B, you can use the formula B is directly proportional to H. B is equal to mu into H. Mu itself is mu naught into mu R into H. So mu naught into mu R into H. What is mu naught? Is 4 pi into 10 to the power minus 7. What is mu R? Is given in the question is 400. Into H we found out. Just multiply and get this answer. You will get B, whose answer will be in Tesla. And then they are asking for IM, which is called magnetizing current. This is something we didn't learn at all. The magnetizing current is slightly complicated, very interesting concept. This solenoid has got an iron core inside. So there's a medium inside and there's a current. Now the magnetizing current is that extra current that you may have to pass, which was 2 ampere plus an additional current that you have to pass when there is no core. In order to get the magnetic field of this one and the magnetic field of this one to be the same. That is known as a magnetizing current IM. That's an additional current which will pass through. After removing the core also, you still have to get the same magnetic field as the core was. Okay, so the B1. In this you have already calculated B1, but you don't have to do it like that. Let's use this formula. B is, there's a medium, so mu naught into mu R into H. For this is last chapter portion. Is B is equal to mu naught into small n into I, the quarter formula. Correct? Because it's vacuum. I can use the quarter formula. So it's mu naught into small n into I is not I, is 2 plus I. Mu naught and mu naught get cancelled. And mu R I know is 400 into H I know is 2000 is equal to small n into 2 plus, small n is number of turns which is given as 1000 into 2 plus I. So directly I can cancel off this and write it as 800 is equal to 2 plus I. So the additional current is 798 ampere, has to be. Very easy sum, beautiful sum. There's one more sum, last sum for the day, and then this lesson is over. Is this question which is again in the textbook. There's no paper without this sum. Let me take this sum and do it. Is example 5.2. There's no paper without this sum. It's in page number 141. Okay, where this shows a small magnetizing needle placed at the point O. At the point O, there is a magnetic needle which is in this direction. The fact that the needle means nothing but magnet, you know that this is south pole and this is your north pole, because within the magnet goes from south to north. I know this is one magnet that's located here. Now arrow marks are marked everywhere at different position. Let's take Q1. Let's take this position is Q1, which means this is another magnet whose moment has been given, which is from south to north. They are saying this is the, you know, the magnetic moment of this magnet, and you know the magnetic field produced by this magnet. This will be lying on the equatorial line of this magnet. The magnetic field at the equatorial will be north to south, so you will have a magnetic field like this. But the magnetic moment is like this from, in this arrow mark gives the magnetic moment's direction, and angle between M and B is 90 degree. So will there be a torque? Yes, the torque will be maximum. Torque is MB sin 90. For this position Q1, the torque will be maximum. Potential energy will be 0 because minus MB cos 90 is 0. So potential energy itself will be 0. So let's take another position. But what is this? This is magnetic field dot equatorial line. What is equatorial line magnetic field? Is mu naught by 4 pi into 2m by r square minus l square the whole square. And what about m? Is small m into 2l. So like this you can plug in all the formula and write the torque. And potential energy becomes 0 in this position. Let's take another position, Q2. The Q2's position is given here. In this position, the magnetic moment of one bar magnet has been given, which is from south to north. This is another magnet, but there will be a magnetic field due to the first magnet in this position, which will be from north to south again, equatorial line, because this is lying on the equatorial line. Again, the angle is 90 degree, and you can mark the torque. Torque is M cross B. You have to mark the direction. You know the torque is M cross B. What is the direction of the magnetic moment in the first case? Is I cap. It's like this. So it's I cap. And B is downward, which is minus J. And I, J, K. And I cross J is K.
Oh.
And it is minus, so minus K because already existing negative sign. The torque will be along minus K direction. And you can write this value. Okay, so let's look at this position. The torque again will be maximum, and you can write the position. So next one, let's talk about this one. There is another position which is here, which is given as Q4, and the arrow is like this. This is this lying on the axial line of this magnet, right? Axial line, it will be, you know that the bar magnet is south to north. Axial line will be away from the north pole.
Yeah.
So it will be away from the north pole is the magnetic field due to this, and the moment and they are making an angle 180 degree. And the torque will be 0 because sine 180 is 0. Torque is MB sine 180. Sine 180 itself is 0. There is no torque. This magnet will not rotate. Prida.
Yeah.
Then the potential energy is minus MB cos 180. Cos 180 is plus 1 plus MB. This position stands for maximum potential energy or unstable position.
Okay.
புரியுதா அந்த மாதிரி ஒரு பாயிண்ட்லையும் how it works you have to analyze and write. It's such an important question. Please understand the textbook sum, and if you're thorough with all these questions, you kind of very well prepared for the exams. Then there are many other questions given in the example sums in the textbook. You please be clear of. Try to understand everything. The whole lesson is over.